Okay, you're all technologists. You know what this is. Yeah, it's an internet device. It has a secondary use as a telephone. Actually, it might be a tertiary use these days. Apparently, it makes noises when you do that. These have vibrate features. It's a really novel feature that we have in the 21st century. So if you really are expecting that call, then that's how you do it. Okay, that's the technology bit of the talk done. So what am I going to talk about? What am I going to talk about? So that's Michael Caine, 1971. What's that got to do with anything? Get Kata. This was a film that he was in. It's kind of London gangster movie. There was apparently a remake of Get Kata with Sylvester Stallone done in 2000. We do not speak of this. Okay? It's a little bit like Sylvester Stallone and Judge Dredd in '95. We do not speak of that version. It does not exist. Dredd with Carl Urban is the only true canonical version. So, good. So this is what I'm talking about. I'm afraid you don't get me with a shotgun, you get me with this, but it's not quite as cool. But Get Kata, and which came first? The film title, did the title of the talk or the content of the talk? Well, obviously the title of the talk came first. I sat there one day thinking of British movies, and I thought, you know what, there's something funny that could be done here. I wonder if there is a talk. We now have an answer. Yes, there is. Okay, what am I going to talk about? What I'm going to talk about is Kata. Okay, now, it turns out this is a word that has got absorbed into the software craftsmanship community. I think it was originally introduced by Pragmatic Dave, the Pragmatic Programmers, in trying to get this focus, get us to think about what it is that we are doing and practice. Because one of the things that we lack in software development is a sort of form of deliberate practice and focus. It's not that we don't get much practice, but there is the old joke, you know, oh yeah, I've been in this industry 10 years, oh. Or is that 1 year 10 times? Okay, we go round in circles. That's a different form of iteration, okay, it's not very helpful. But we also do not get the opportunity to explore and learn. With most things, particularly in a sort of an educational environment, in a practice environment, you get to repeat things. You get to try things again. You get to perfect them. If you play a musical instrument or you undertake a sport, you know that you do the same thing again to perfect it, to try it. So the idea of a kata is the repetition. In software development is filled with things that are kind of like other things, but they're not identical. And once you've mastered them, or you think you're just about to master them, you move on to the next piece of software. In other words, you try something, I think I've got it. Oh, okay, we've shipped it, and now I've got to move on to something else. So the idea of the kata is actually to slow you down, to make you focus on what you're doing, and to choose something very small. Now, the term is Japanese, and it has a couple of ways of being transcribed. You know, so I clearly did my homework, and you've got the kana form, then it has two kanji forms, that one and that one. I do not know enough Japanese, as in, I know this much Japanese. Actually, I probably know more Japanese than I do Hebrew, to be fair. But there are two forms. I'm not entirely sure what the preferred one is. But in terms of pronunciation, there are lots of different pronunciations people try to use. Kata, actually it does come out as kata. Kata is closer to its supposedly true pronunciation. But there are various translations. Form is one of them. It's about structure. It's about the form of what you're doing, structure in space and structure in time. It is applied in martial arts as a practice form, so it covers both of these concepts. Pattern, which is very dear to my heart. I've co-authored a couple of books on patterns. I find the pattern way of thinking is a very profound way of approaching problems and solving them, reasoning through forces, thinking about context. Unfortunately, that's not the bit that people normally associate with patterns because it's hard. And like most things that are hard, people ignore the hard bit and go for the easy bit. Style. There is this idea that a collection of patterns gives you a style. Patterns originated in building architecture. We use the term architectural style and pattern almost interchangeably. And there's an idea there that if you do something in a particular way, you create a particular result. You cannot separate the way that you do something from the thing that comes out at the other end. And then training exercise, which is the most common idea, from martial arts into the software craftsmanship community. It is normally associated with really getting into test-first programming. But I'm not really going to talk exactly about that. What I want to talk about is a very sort of simple idea. First of all, the deliberate practice approach, but then I want to go beyond the deliberate practice approach. So this is a book I edited a few years ago, 97 Things Every Programmer Should Know. My friend John Jagger had this entry, do lots of deliberate practice. And this is the focus, deliberate practice. This is what we're after. You do deliberate practice to improve your ability to perform a task. It's about skill and technique. It means repetition. It is not about completing the task. It is about mastering the task, which is different. Your daily work is about completion. The goal here is mastery. It's fundamentally different. You have to slow down and stop. But I'm also interested in something else. I'm interested in the idea that a kata is almost a small laboratory. It is a laboratory which, when you understand it, well, what do you do in laboratories? You experiment. You try things out. Émile Auguste Chartier, this lovely quote, probably one of my favorite all-purpose quotes, nothing is more dangerous than an idea when you have only one idea. Okay? You feel free to use this throughout your whole life. Okay? You can leave now if this is the most important thing you're going to learn this evening. Okay? But there is this. We normally, as developers, have a very bad habit of doing a first fit. In other words, yep, I've got it. Okay, let's do it that way. And it's just like, oh, okay, that's the first idea you had. What about the second idea? No, 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 this is fine. Well, how do you know? It turns out one of the things that humans are reasonably good at, although apparently in the UK and in the US, we seem to be struggling with this idea of comparing things. Normally, we're quite good when given two choices, most humans, with the exemption of, yeah, the UK and the US. When given two options, we're normally quite good at comparing them. How do you know that's a good idea? Give me your second idea. What's your third idea? Yeah? The first idea is also something that may have just come out. It's just like, yeah, it's clearing your brain. Okay? The second idea might be better. It might be worse, but you won't know until you get to compare them. Experiment. How do you experiment? Well, I'm going to take our large product and start experimenting on that. Oh, easy there. Maybe you don't want to do the big experiment like that. Maybe just try small things. A kata is an opportunity to experiment. And the smallest elements of style. And this is really important. I think people often overlook this idea. Often people talk about software, they look at coding practice, and they say, oh, that's just a small detail. And I always come back to them and say, well, what do you think software is? That's the whole point of software. Software is all about the details. All the rest is the stuff that happens in meetings, it's the hand waving, and then you have detail. And a working software system is lots of details put together so they work. That is the whole point of software. Okay? Everything else is just conversation. So there is this idea there is no such thing as a detail that is too small. And particularly one of the things you may observe is that as a software system grows, as parts of it grow, we experience what is known as an inflationary phase. In other words, those small little ripples in that tiny, tiny method that you once wrote, that you didn't pay much attention to, when it got maintained and grown and extended and grown, those little ripples suddenly became the galaxies of your system. Okay? You can normally trace back the warts, the weird bits, the technical debt locales to something that somebody did and then somebody else followed through, and then they followed through. They normally grew out of a small detail. So details matter, and we often find that the large-scale architectures reflect ideas in the small. So I want to just start off from somewhere completely different and demonstrate the value of different ideas and lateral thinking. So this is a right-angled triangle. Wow. Okay, anybody want to take a guess at what dimensions I might have chosen?
1, 2,
3, 4, 5. Yeah. So 3, 4, 5. Which, you know, we're going to be mathematical. We don't use numbers in maths. That's for arithmeticians. Real mathematicians don't use numbers. Okay, so, well, they do, powers. There you go. So we've got this whole idea, Pythagoras, brilliant. If you want to do it visually, you have this. Now, there is a thought here. Everybody learned this at one point or another. And you may also have learned a proof. I learnt a proof at school. I think the first proof I was shown was a proof by similar triangles.
That's Einstein's proof. That's Einstein's proof.
No, he did a different one. He did do one. He did a dissection one. The similar angles. Huh?
He does the one line to get to the, he does the shortest amplitude.
That's a different one. Yeah, there are about 400, it turns out. This is what I discovered when I started digging into this topic. Yeah, Einstein does a slightly different approach, but it wasn't it wasn't that one that I was taught at school. But there is an interesting question here. What the hell did Pythagoras do? I mean, you know, a very obvious thing. Pythagoras is not going to use the Roman alphabet. That's the first observation. When did this notation come about? Yeah, the equal sign is actually quite young. It's a couple of centuries old.
The squaring is very young.
The squaring is really young. So, how did this whole algebra concept, that's really, yeah. What did he do? He clearly didn't do it like this. So, this is a sort of this is the kind of basic kind of approach. He did a proof by rearrangement. Because that you can do. Standing there with your stick and the sand or tiles, you can do the proof by rearrangement, move it around, and then logically you can say, and you can call them whatever you like. So this is the original proof, was a proof by rearrangement. We move things around. There are actually quite a few proofs by rearrangement, it turns out. So, yeah, that all works. My favorite one is probably my favorite algebraic one, or most memorable one, there's a number of variations, is this. And the observation that if those are C, then, and those are, that's A, that's B, therefore this must be like that. You get C squared plus B squared, therefore this is A plus B plus, brilliant. And so we get this, and you cancel things out, and magic happens. Marvelous. That's the second way, it's completely different. But my recent favorite, I discovered this December last year, is this one. The trapezoid one. This one was proven by President Garfield of the United States. The 23rd president, I think he was, of the US. I just want you to compare that with number 45, the current incumbent. President Garfield, well, actually it was just before he became president. He wasn't president very long. It was back when assassinations were popular. But in the 1870s, when he was a senator, I believe, he came up with an original proof. Yeah, standards have fallen, okay? But yeah, very, very simple idea. It's just like, well, if those are C on each side, then it's just like, okay, this is really very elegant. It all works out beautifully. And boom, you've got this. You have to know a little bit about areas, but that's fine. And the right things happen. The halves disappear, and you've got it. So 3 approaches, and as I said, it was almost a rite of passage. Everybody's got to have their own. Okay, so yeah, Einstein did one. Everybody did one except every president after Garfield. But as I said, there seem to be nearly 400. There might be more, but apparently there was a book published in the 1960s that had about 350. So I'm presuming somebody's come up with a few since then. And these are different ways of looking at the same thing. Now, what is interesting about them is that they have different appeals to different people. A proof by rearrangement is something that you can demonstrate just on a table. And it's quite elegant from that point of view. The previous algebraic proof I managed to show to my younger son when he was 10, and he got it. And it's just a case of like, what is it that appeals? Everybody finds a different simplicity and a different way of looking at something. So what are we going to do? We're going to look at a real enterprise problem here, Fizzbuzz, okay? And this is the heart of every major system, of course. So as a number of you have beer in your hands, just check. Who is familiar with Fizzbuzz? Okay, let's try that one again. Who's not familiar with Fizzbuzz? Okay, good. There are a few people. Okay, Fizzbuzz is a counting game. Okay, it's relatively simple. You go group of friends, group of enemies. It doesn't really matter. Actually, it might be a good way to settle international conflicts. 1, 2, fizz. Every number divisible by 3 is replaced by fizz. 4, buzz. Every number divisible by 5 is replaced by buzz. Fizz, 7, 8, 9. I got it wrong, take a drink. Okay? If you do not have a drink, it is really not very exciting. Okay? Yeah, my wife and my sons, we were on holiday last year, and we were waiting for food in a restaurant. They had not yet served us the wine. Both my boys, they are mathematically, good. Both the adults were sober, and we've played this game waiting for the food. It is really boring. Everybody gets everything right, okay? Because the only quirk is that every number divisible by 3 and 5, in other words 15, is replaced by Fizzbuzz. 13, 14, Fizzbuzz. 16, 17, Fizz, 19, Buzz. Okay. Somewhere along the line, somebody decided this would be a good interview question for programmers. Actually, it's not a bad interview question. You might be surprised how many people struggle with it. And it's also become a kind of rite of passage in the software craftsmanship community. Can you TDD this? So what I'm going to do is we'll just sort of pick on a relatively simple implementation, one that is very much structured in terms of accumulator. The idea of accumulating, it's a fairly sequential approach, but people normally eventually come across this, and they are sort of happy at the basic elegance that fizzbuzzness is an emergent property. You only ever have to care about fizz and buzz, and the rest happens by magic. But you are dealing with accumulated state. Okay, so that works. Alternatively, we have something that uses tail return. Everything has a mutually exclusive path. Everything is handled. And if your friend's kind of saying, hey, you should do more functional, no, this is more functional. There's no kind of like state changes. There's no variables. So you can say, yeah, this is functional. Your friend comes along and goes, that's not functional. Come on, man. Come on, that's functional, okay? It's got to be an expression. You're using statements. And you go, yeah, you know what? Yeah, you're right. I can see that. But then start thinking differently, okay? Because is it an arithmetic problem? Is it an arithmetic problem? Are we dividing things by 3? Are we asking the question, is it divisible by 3? Is it divisible by... Can we invert that and say, actually, I've got a set of numbers. By the way, just in case you're wondering about the upper limit, the problem is normally specified over the domain of 1 to 100. Because people are either way too drunk by that point or just bored out of their tiny minds. But from a programmer's point of view, that's normally the way it's specified. So you've got this. So what we're going to do here is we're going to turn it around. We're going to invert it. We're going to say, look, I'm going to have the set of numbers that are the 15s. So 15, 30, 45. If this number is in that set, then how? It's Fizzbuzz. If it's in the set of 3s, so I'm going to turn the problem around. Instead of thinking of it as a problem of I'm applying an operation, a divisibility operation to something, I'm going to turn it around into set membership. Okay? And so this changes the shape of the problem ever so slightly. Here's another one. So what I'm going to do here is I'm going to say, why don't we construct this and recover our emergent property, which was quite nice before, do something slightly different. The stopper at the beginning and the end are just to align numbers and zero-based counting. I want to count from 1. But the other way of looking at it is to ask a very simple question. Show me all the fizzes. Okay? Between here and 100, where do the fizzes occur? Well, the fizzes are every 3. So that's blank, blank, fizz, blank, blank, fizz, blank, blank, fizz. Please generate that for me. So that's another way of doing it. So I'm going to do that, and I'm going to index that. The buzzes, 4 blanks and a buzz. Repeat as necessary. Okay, now what I'm going to do is, what are all the numbers between 1 and 100? But as strings. Okay, so now I'm going to stringify all the numbers. So I've got 1, 2, 3. So now I've got all the resources I'll ever need. Okay, I've got numbers and I've got words. And then I compose them together. I take the fizz, I take the buzz, I concatenate them. If there's something there, we either have fizz, buzz, or fizz, buzz. If there isn't, and I've got to love Python for this, Python has a very kind of loose relationship with the whole idea of Booleanness. It's quite good. It's, it's either really good or you really hate it. Okay, it's something that lives at one of 2 extremes. So it's a case of like, well, if there was something there, then we're good with it. Otherwise, get one of those numbers, and we're good. Okay, so that's a different way of looking at it. And then your friend comes along and says, no, it's got to be about lambdas. Kevlin, you've got to have lambdas. And Python is one of those languages that couldn't come up with a short notation for lambdas. They really struggled with the spelling of it, so they spelt it lambda. Every other language that uses lambdas, with possible exception of Lisp, actually does not spell it out lambda. They come up with some kind of crazy notation, okay? And it's like a competition between languages. What are you going to do? Well, I'm going to use a little equals sign followed by an arrow. Oh, okay, okay. Well, I'm going to use square brackets and an emoji. Oh, cool. You know, so there's like a competition. Python was terribly dull. It's just like, yeah, it's called lambda. Oh, okay, right. So we're going to have lambdas for fizz, buzzed, numbered. This is probably enough to get you excommunicated from the Python community because it's not very Pythonic. But we're also going to mess about, you know, explore the languages a bit, kick the tires of it, okay? Python is a language, as I said, it has a very loose relationship with the concept of Booleanness. It also has some very interesting relationships with numbers. So n mod 3 equals 0. Well, that's going to be either true or false. Okay, so false times a string is empty string. True times a string is the identity operation. It's the string. Brilliant. So we can actually do Boolean multiplication of strings. Excellent. Yeah? So we've got that. That's fantastic. So now we've got all of this stuff, and then we just combine it. And this is pure addition. Okay? It's just like, yeah, this is really nice. Okay? Really nice, or you really hate it. There's this one, which combines it all into one, although it turns out when we realize we can do that. I like this one because you can put it in a tweet with a comment. Okay? Just sort of say, you know, yes. So this is it. It's great. So we can really mess about with this. But the question comes, yeah, Kevlin, that's Python. These are all small examples. I work in an enterprise environment. Okay. There is, of course, Fizzbuzz Enterprise Edition. If you have not come across this, go and spend some time looking at this, and then run away very, very fast. Now, I'm clear, I'm of a particular generation and inclination that I still cannot do this. I still, you know, it doesn't matter that the whole Java Enterprise thing kicked off 20 years ago. The word enterprise, I only think of one thing. You know, I still, you know, 2 decades on, you say enterprise and whoop, Captain Kirk pops into my head and I'm thinking NCC 1701. Or am I thinking NCC 1701A? Maybe B, maybe C, maybe D, maybe the reboot. I really love this. It's beautiful. It's gorgeous. It's a lot better than most enterprise software I have ever seen. Okay? But there is something here that is true and deep and profound and physically possible that gives us a road into understanding this. It turns out that NASA have actually been looking into warp drive, although don't pack your bags for Proxima Centauri just yet. There is actually a research group that looks into this, and naturally enough, they named this is one of the artist mock-ups of what a craft would look like, Enterprise, because it actually turns out that there is a possibility of warp drive. Okay, Miguel Alcubierre, Mexican physicist, 1994. Explored the equations of general relativity and came to the conclusion that it was actually possible to warp space in a way that allowed you to travel faster. Okay, so there is a basic. Einstein got a mention earlier on. He's probably not that well known for his Pythagorean proof. He's probably a little better known for his theories of relativity. And there is this solution that allows you to get around, or seemingly get around, this whole issue of the speed of light being a bit of a speed limit. It's the speed of light in a vacuum, or to be precise, the speed of light in space-time. Okay? Now, you can't go faster than that. But here's the clever bit. If you can make space-time move, then you still respect the law. In other words, if I say, well, I'm still traveling less than the speed of light in space-time, but somebody else is moving space-time for me, and it's faster, notice it's a beautiful illusion. We have warped reality. Now you understand the relationship to enterprise software. Okay? It is a reality distortion field. There are a couple of small issues with Miguel Alcubierre's theory when it comes to what they call an implementation detail. Remember I said there are no details? The idea here is these are actually warp coils. This is actually, there is an idea that you hold this. This will warp the space around the craft. Okay? And what are these filled with? They are filled with exotic matter. We don't actually know that that stuff exists. And if it does exist, we don't know how to make it. We're not entirely sure how much we would need. One estimate says you might need to condense the mass of the moon into these warp coils. These are small details. Okay, you know, if you're a manager, yeah, this is it. It's just a detail. However, it does return us to the reality or the distorted reality of enterprise software. And I do strongly recommend, as I say, going and having a look at this thing. Enterprise software marks a special high-grade class of software that makes careful use of relevant software architecture design principles to build particularly customizable and extensible solutions to real problems. By the way, just in case you know you've had a long day and your sense of humor is failing at this point, this is a spoof site, or rather it's intended as humor. I did have to clarify that to one person. Perhaps they've just had a really hard time in the industry and that this actually looks quite plausible. Yeah, hire him. Yeah, you got a job. This project is an example of how the popular Fizzbuzz game might be built, where it's subject to the high-quality standards of enterprise software. And you know, you can just wander through the Git repo, and you know, it's got all the really good stuff. You know, people are actually there are commits to this. You've got a fizz string returner factory. You've got an integer printer returner factory. You've got a no Fizzbuzz, no buzz strategy factory. And you know, so this is as you can tell, this is just the factory stuff, okay? There's a whole code base out there of possibilities. Yes?
Where's the open pull request from 2 months ago?
That's a very good question. This screen grab was a few months before that. But yeah, it's absolutely magnificent. You don't want this in your code base. Paul Anderson, science fiction author. I have yet to see any problem, however complicated, which when you looked at it in the right way did not become still more complicated. This is a really useful thing. I think secretly all programmers know this. They just didn't know that they knew this. This is kind of like there's a deep belief. I see that problem that you've set me, I can make it more complex. Yeah? Oh yeah, that's a really easy requirement, but if I added this, it would make it interesting. Okay, we're always playing. So there's a certain playfulness. But I do want to channel the playfulness into a different form of experimentation. You can do this with different models. So this is an awk solution. I quite like awk. It's a language that is much neglected these days. Partly, it had a bit of a fight with Perl in the 1990s and lost. As a friend of mine described Perl as being executable line noise. I've never moved from that belief. But awk has a very dedicated view. It is about pattern matching, and it is structured around that. In other words, you don't have a loop to loop over your input. There just is input. You are part of a stream, and this is invoked every single time. You don't need to repeat the fact. So there's a little more, it's a little more of an implicit invocation environment. It's got a slightly different execution model to what you might find in other imperative languages. So what I'm doing here simply is just matching. Is it divisible by 3, by 5, by not by 3 and by 5, and then for all cases I will print out this matches, the last one always matches, and we print out a new line. Now, how do we test this? How do we drive it? Well, to drive it, it's fairly easy. We use that old functional programming technique called the shell. People often overlook the fact that a shell environment, a pipeline environment, is actually a data flow architecture, which is a particular form of concatenative programming. And this generates this quite nicely. And if you want to test it, we can just pump it into there. Now, it turns out this problem is small enough that we don't necessarily need to define all the properties, because we're only doing it up to 100. You can generate all the values by going around the table, sober. So we can actually just cat the file, and there it is. Yeah, just diff against it. If you have a small enough set, this actually works out fine. So why have I picked on awk? Well, for a number of reasons. One, I think it's a much neglected language. Two, there's an unusual solution for this. And three, it's the oldest example of test-first programming I've been able to find. Alfred Aho, who is the A in awk, Aho, Weinberger, Kernighan, when he was interviewed, and he made an observation about how they developed this in the 1970s. We instituted a rigorous regression test for all the features of awk. By the way, the lead up to this story is that it had a bug. So there's a question of like, well, what do we do now? They decided that the only way to get complete coverage and guarantee that you have the best coverage possible is to always have more coverage than code. How is that possible? Well, you write your tests first. Therefore, by definition, you are covering things that you do not yet have. Yeah? So I know it's a kind of it's a normal football manager thing to say, you know, our footballers gave it 110%. You know, the guys gave it 110%. That's the whole point of TDD. You give it 110%. What's your coverage? 110% at the moment. It's like, oh, okay, it fails, doesn't it? Yeah, because that's a fancy way of saying it fails. So next time you have a red, you can now translate that into 110%. You can give coverage figures that are higher than reasonable. Okay, you can exceed the limits like the speed of light and so on. Any of the three of us who put in a new feature into the language first had to write a test for the new feature. This is test-first programming, 1970s style. Okay, so it turns out that test-first programming, TDD, and all this stuff has a long prehistory. It was just very scattered. And then it kind of started coming together with XP, and it became an entity in its own right. But up until that, it's not that it was unknown, it just was edge cases. So here's how people normally present the test-first cycle. Red, green, refactor. And a lot of people, when they arrive at this, they're not entirely sure about it. And so they kind of go, well, you know, I don't really see the point, because write a failing test. Well, anybody can do that. I mean, you know, where's the skill in that? Yeah, I can write a failing test with my eyes closed. So there's no skill in that. So the problem is, I find when people run this stuff, they often end up spending a lot of time on green. They're trying to get to green. It's like, no, you need to show what you're going to do. The idea is to show what you're going to do. Red, green, refactor. Now, when people start getting the rhythm, red, green, they keep forgetting about this bit. It's below the line. So you end up with the dumbed down version. I got a failing test. I write just enough code to make it pass. And then I write another test case. Then I write another piece of code to make it pass. We miss out that bit. And then we end up with some really crazy code. And we say, this test-first stuff, it doesn't really work. And unfortunately, that kind of view, although Uncle Bob didn't mean to put it like this, his 3 laws of TDD, and these are not laws that anybody's going to come around and knock on your door and go, I'm afraid you've broken the law. These are not physics laws. You can actually break them. It's quite easy. We do it every day. These are but 3 guidelines. Okay. 1, you are not allowed to write any production code unless it is to make a failing unit test pass. 2, you are not allowed to write any more of a unit test than is sufficient to fail, and compilation failures are failures. 3, you are not allowed to write any more production code than is sufficient to pass the 1 failing unit test. It turns out we actually need 4 because this is not enough. What happens if I just follow these? Well, actually, I get this. So what does that look like in practice? Okay, let's do Fizzbuzz. Right, we're going to build it up this time, okay? Assert Fizzbuzz of 1 is 1. Brilliant. How do I pass that? Brilliant. Done. Assert Fizzbuzz of 2 is 2. How do I pass that? Yeah. Copy, paste, copy, paste. This is the other kind of enterprise programming. Yeah, it's not the one that is architecturally complex. It is the one that is pure copy and paste. And it's brilliant because your productivity is awesome in one day. Okay, because I've done this. Okay, how are you doing? Let's just tidy it up so we feel there's a sort of elegant regularity. Boom, done. Go home. How are you doing? 100 lines of code today. Yeah? Does it work? 101. You're right. You're right. I get a free one as well. That's great. So 101 lines of code that works because we had tests. How many lines of tests did you have? 100. So you wrote 201 lines of code that works today. Brilliant. Yeah, excellent. Have you reviewed it? No. Has anybody else reviewed it? No. So then you go home. You think about this, and you think, you know what? I'm not using all my techniques. I'm not using all my education. I'm not using all my brain power. You know what I need? I need lambdas. Yes. Brilliant. I need lambdas and I need lookups. This is how we do it. This is how we do it. It's a dictionary. It's a lookup. I've been told to make my code more declarative. I've been told that I need to get more functional. Magnificent. You know, that's a work of art. And then your colleague comes along and says, yeah, actually. And in fact, if we think about it, it's not really that exciting. But that's a terrible solution. This is the point. This is the bit here. You're supposed to bring your brain to the party. I don't actually like this as a way of describing the test-first approach or the philosophy of TDD. I prefer anchoring it in something slightly different. I prefer the Deming-Shewhart cycle, which people normally associate with lean or agile thinking and at the large. PDSA originated with Shewhart, was popularized by Deming. The variation is that plan, do, check, act, but I find the study term is more important because study sounds slow. Study has the same first 2 letters as stop, okay? Coincidence? I think not. Okay, the idea is slow down, study. Check is very cursory. It's just like, yeah, checked it, it's good. Study suggests you use your brain. This is very hard. Well, the evidence suggests it's very hard. This is the bit that is below the waterline. Plan and do are highly visible. Study and act, they don't have substance, so they're quite difficult to pin down. But it turns out that if you want to run an experimental life cycle, if you want to experiment in the large, this is the most important bit. People are always planning, doing, planning, doing, planning, doing. But the reaction about, well, how did that work out? Why did it not work out? Give me 3 theories. Don't just give me 1, give me 3. Okay, rule of 3. Nothing is more dangerous than an idea when you have only 1. 2 is a good start. 3, well, now it becomes difficult to stop. Once you've got 3, you'll get 4. So the point here is this is the hardest part to do. This is the bit we normally focus on, the plan and the do, whether it is user stories, sprint velocities, or whatever it is, because it's visible. This is hardly visible at all, but it's the bit that makes the difference. If you're going to experiment and try new things, you need this lower part. So what has this got to do with TDD? Why do I think there's a better way of describing the test-first cycle? Because if you can do it exactly the same way. Plan what you're going to do. Oh, that's the test. Here's the test for the code this is the behavior that I want. This is what I'm about to write. This is what it looks like, or at least what I think it looks like. I would like this to work. It's a pull-driven approach. I'm going to pull from the ether, or at least my brain. I'm going to pull out an idea. It should look like this. Let me implement it. Let me do it. Let me reify it. Reify is to make real. Okay, make it substance. Okay, I sketch out a test or a spec, and then I make it real. And then I reflect on it. And as necessary, I refactor. So there's this kind of idea of like, when you look at it like that, it's like, oh, okay, that's why it makes sense. Red-green refactor, it sounds kind of catchy, but it's actually, it doesn't quite get you thinking. This is about thinking, okay? It turns out this is mostly about slowing down. Yeah? If software development were based on typing speed, we would have solved that problem decades ago. Okay? It turns out this bit is the hard bit. It's having solutions. It's the idea of being able to pause and think every now and then. So let's try a different way of doing this. Okay? So I've got an actual. So here's a list of all the Fizzbuzzes from 1 to 100. So I'm going to try a different way of testing it. And there are lots of different varieties of testing. One is obviously that you have a sample of here are all the possible outcomes. It turns out for 100 values, that is certainly doable. But when somebody says enterprise system, which can have trillions or quadrillions of different states, it turns out this is less than practical. So therefore, you need a different way of reasoning about it. So let's just try a different approach. Not example-based, I'm going to take a property-based approach. I'm going to have an array or a list of truths. Okay? There are things that must be true of the actual result for it to be a successful Fizzbuzz. Okay, and what I'm going to do is assert all truths. What do the truths look like? Well, every result is Fizzbuzz, Fizzbuzz, or a decimal string. Every decimal result corresponds to its ordinal position. Every third result contains fizz. Every fifth result contains buzz, and every 15th result is Fizzbuzz. This is necessary, but it's not sufficient. It turns out you need another 3 conditions. The ordinal position of every fizz result is divisible by 3. The ordinal position of every buzz result, divisible by 5. Ordinal position of every Fizzbuzz, divisible by 15. And now we discover the reason that I chose Python is because it turns out it's quite easy to convert into Python. So therefore, we have a very simple concept of here are all the truths that characterize this. Okay? So this allows you to experiment in the small with like, how good am I at discovering how to articulate the truths? Now, you might want a framework at this point to make this a little easier, but the basic mechanics, if you like this very raw approach, a lot of people assume that TDD is about frameworks and things like that. It isn't. The framework extends the reach. It extends the reach of your thinking, but if you don't have the thinking, then you just have, you're a fool with a tool, unfortunately. And I don't want to say that of you. That's obviously your colleagues, not you, because you turned up, okay? Oh, yeah, and your bosses, so they were your colleagues, but they got promoted because they weren't good enough, so stuff like that. So the point here is that it's the idea that there is, do I understand the idea? Do I understand what I want from the framework? And then it's just like, yeah, I do. This is the philosophy of take it apart to understand how it works. And it's really good if you put it back together again, but you know, taking it apart is fun. In fact, taking it apart is fundamental. Decomposition is the basis. But there's another side of this, composition. And one of the most composable approaches that we tend to think of these days, people are focused very much on functional programming as a model of composability. And I stumbled across this paper by Maciej Pirog, and apologies if I pronounced his name incorrectly, Fizzbuzz in Haskell by embedding a domain-specific language. It's like, yeah, there's some really mental stuff in this paper. It's, you know, yeah. However, I'm just going to extract a small observation here and then take one of his results and do it slightly differently. The default action is executed only if some previous actions were not executed. This is true of everything that we've done. Okay, so we looked at some programming languages. For a bit of variety, we're going to look at JavaScript. Yes, I did say that. There we go. This is the first solution, just done as done again in JavaScript, and you can see we are doing default action, which is print a number or generate a number, only if some previous actions were not generated. Okay, there's our stop. So there's a kind of like, yeah, that's a shame. I can even get crazy with it. Let's do this by lookup. Okay. Yeah, so when you're bored in the office tomorrow and you want to replace all those if statements, yeah, you know, why not? You know, this is a great way of doing it. That great was in quotes, by the way. I'm not recommending this. However, we have a table lookup approach. But again, the default action, n2 string, is only executed if there's a branch here. It may look like an is piece of notation, but there is a conditional branch. And he makes the observation, ask the question, can we accomplish this without having to check the conditions for previous actions twice? In other words, can we make the control flow follow the information flow without losing modularity? And he explores this in great depth. I'm not going to explore it in great depth, but I'll give you, I did this in a few languages. It was quite good fun re-implementing this in different languages, seeing how easy it was in some languages versus how hard. Curiously enough, Java was actually the hardest. The notation was really simple for the lambdas, but it's an absolute nightmare to get the declarations right. And it's just like you're sitting there and you've got the declarations, and then somewhere over on the right-hand side of the screen is the little lambda expression that is oh so tiny and short. Out to the left is this really long preamble that you're going to ignore because it really isn't very interesting. What we're going to do is we're going to have a lambda called test. It's going to take the divisor, it's going to take a string, and it's going to take something we can execute. And what we're going to do is we're going to have a fizz that takes something that it can execute, in other words, another function. And we're going to test. And depending on whether or not the number n is divisible by 3, we're going to make a decision. And what we're going to do is we're going to decide, we're going to compose with another lambda. So you end up with this beautiful expression at the end. This is the identity operation that all works. It's great. Anyway, I recommend you go and look at the paper and have a go in your language of choice as to this, or drop me a line for the, drop me an email for this code. I might put it up on SlideShare just so you can have a bit of fun with it. But yeah, try it in different languages. Find out what they feel like. For me, I think in terms of regular languages, Python and Groovy were the easiest. I found most languages, most mainstream languages with an opinion on types are actually quite difficult by comparison. Anyway, Oscar Wilde. I'm not recommending this as practical. This is pure art. Except, is it? I mean, there's a lot of ideas in here that are quite profound. But let's look at another way. There is another way. Let's make a very simple observation. Let's encode this. Okay? So let's encode this. Here we have a list. 0 means it's the default. It's the number. 1 means fizz. 2 means buzz. 3 means fizzbuzz. Okay, that's what it looks like, and then it just repeats. Okay, so that's the basic model. Okay, so we've encoded it. What I'm going to do is I'm going to shift it round one so that all the indexing works from 0. And then, yeah, you could do this. So a little bit of Ruby here. 100, we map I into that, and then we do this over here. Bit of modular arithmetic, and magic, this works. But here's the really crazy thing. If you ever want to have a conversation with somebody about random numbers, and you say, you know, those random numbers, they're not really random, you do this. So this blog I came across, somebody recommended this to me because I talk about Fizzbuzz often enough that people send me crazy solutions. Absolutely magnificent. This guy basically searched the rand space, basically searched, seeded and searched for that little sequence that I just showed there. Where does this sequence occur? Okay? And there it is for round 4. And that's the sequence, so that's the magic number. Okay? At that point, you will get a nice repeatable implementation, as long as nobody changes the implementation of srand and rand. So, so this is what we're talking about. You might think, wait a minute, that Émile Auguste Chartier quote, maybe it is too dangerous to have more than one idea if this is the kind of idea you're coming up with, Kevlin. I know, but it's fun. This is the whole point. It's enjoyable. Then I guess we ought to have a look at Haskell. This is a variation of a solution I originally saw from Dirk Koenig, who's responsible for the Frege language on the JVM. And the way to introduce it is actually to return to one of the earlier observations about, or one of the earlier examples I had in Python. But you know, originally the problem was limited to a domain of 100. Why don't we just let go of the limits a little bit? Fizzes. This is all the fizzes you will ever need. Blank, blank, fizz, blank, blank, fizz, blank, blank, fizz, blank, blank, fizz, blank, blank. How many of them? Infinite. And you're sitting there going like, let's see, how much memory do I have on my laptop? Yeah, infinite, okay? Here's all the buzzes you'll ever need. Okay, blank, 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 buzz. Repeat until infinity. So this slide currently contains 2 infinities. Oh, this is great. This slide has got a lot of capacity because here's the 3rd infinity. I'm going to take those 2 infinities and I'm going to merge them. Okay, I'm going to zip them together. So what I've got now is blank, blank, fizz, blank, buzz. Fizz, blank, blank, fizz, buzz, where it's necessary. Okay, so these are all the words we will ever need. 4 infinities. These are all the numbers, stringified, we will ever need. 1, 2, 3. 4 infinities. Yeah, you never knew PowerPoint could take that. And now we have to make a decision. Number or word? Number or word? And then we compose it, so we get Fizzbuzz. What's interesting here is we're not actually defining any new functions in this. This is actually, that Fizzbuzz is an infinite sequence, okay? Or semi-infinite, because we know where it starts, okay? It starts at 1, then it goes 2, then it goes fizz, then it goes 4, and it just goes on and on and on to infinity. Okay? What we do is we apply our choice to the words and the numbers, we choose between them, and then we just zip all the way down, making that choice. It's nice. Okay, here's how we get away with it, because it turns out that the best way to understand this infinitude, which normally has to be expressed using enumerators or iterators in other languages, is that this is all about laziness, or another way of putting it is it's hypotheticals. Let me clarify what I mean by that. Because what we're going to do is blank, blank, fizz, we're going to cycle it from here to infinity. Buzzes, we're going to cycle that from here to infinity. Words, it looks like we're actually going to do some work, but this is the clever bit. This is how the lazy evaluation side of functional programming works. It's so lazy it doesn't happen. It's kind of like a promise. It's like an idea. It's just like, if I were, so this is the way you do it. This is how Haskell gets around things like side effects and how functional programming gets around it. It's a very clever way just for side effects, for I/O, for example. The way to reason about it is to say, in a pure functional language, you cannot have side effects because these are pure functions. But let me describe to you how I would do I/O. I'm not doing it. Oh, no. Doing is an imperative thing. But if I were to do it, notice I'm being very careful. There's an extra level of indirection in what I'm saying. If I were to do I/O, it would look like this, but I'm not doing I/O. But it would look like this. Ah, clever. And then you hand this off to the runtime. But you are still pure. Yeah, clever. It's an outsourcing trick. Okay? You outsource the state changes. You just describe it as if you were going to do it. If I were to have infinite sequences, this is how you would do it. Yeah. If I were to calculate all the words, this is how I would do it. If I wanted all the numbers, I would take them. This is stringify. I'm going to apply the string operation from 1 to infinity, if I were to do it, it would look like this. Are you going to do it? Well, I never said I was going to do it. I'm just telling you how I might do it. Classic mathematician approach. Yeah? Choice is either profoundly elegant or a real hack, depending on your point of view. I think it's really elegant. I was very pleased with this. It turns out the numbers order perfectly with respect to the letters. Yeah? Or rather, so this actually works out based on any character set you care to name on which there is a Haskell compiler. Because I did have somebody say, yeah, but what if your character set doesn't do the right thing? I will buy you a meal if you can find a Haskell implementation on a platform that has a character set that disobeys this.
Can they hack it for non-lexical breath ordering?
No, you can't hack it. No, it's good.
Worth a sandwich?
Didn't say sandwich, said meal.
Yeah, no, you're getting me the meal. Yeah, this is it. I might give you an olive, okay? You know, okay. Okay, so this is how we do it. So this is all hypothetical. Nothing's actually happened here. We just made a bunch of promises. At this point, we actually do some work. Give me the first 100. At this point, we actually have an imperative statement, or Haskell programs will tell you it's not imperative. Trust me, I know language. Take is, and I've got kids, take is a very strong stateful operation, okay? Okay. At this point, we're going to make a commitment. Give me the first 100. At this point, something actually happens. Up until this point, nothing has happened. Yeah? Yeah? So this is why it's called declarative. I do declare this. Have you done anything? Absolutely nothing at all. Yeah? So, but it's a very elegant way of looking at the problem. And this kind of stream-based thinking, this kind of infinite thinking, this kind of idea of operations on things, is both profound but also quite amusing. This quote from 2009, I love functional programming. It takes smart people who would otherwise be competing with me and turns them into unemployable crazies. It's because you see that is the problem when you start looking, you know, this is the kind of classic Nietzsche, if you look into the abyss will stare back at you. There are 4 infinities on this slide. No, I'm wrong, 5 infinities, I forgot this one. There are 5 infinities. You cannot look at infinity without having some kind of reality distortion. You go crazy at this. Okay, I think I've got just enough time for a couple more things, haven't I? Yeah, so let's look at another Kata. I'm going to do something slightly different with that. I said I know a little bit about words, I know a little bit about words, and so therefore, one of the things I do is I run a page, Word Friday, on Facebook, and every Friday I present an unusual word and a definition. The rest of the week is just language and linguistic stuff that I find interesting, that I found on the web. The reason this is relevant is one of the words I featured a couple of years ago is biquinary coded decimal. Okay, you get bonus points if you can drop that into a conversation naturally tomorrow. Okay, I do actually know somebody who always checks my Word Friday stuff and sees if he can get it into a conversation over the weekend. You know, just get the word in. You know, sometimes it's quite a challenge. Sometimes you can do it ordinarily. Yes.
I learned a new word yesterday. It was biquinary coded decimals. There you go.
There you go. That's perfect. You know, but you need to be more discreet. You need to somehow just slip it in as if there were.
I learned a word.
Oh yeah, this is it. Or do it as a promise. Do it as a kind of like a declarative approach. We've learned all about that. So here, biquinary coded decimal.
Ask me about the word I learned yesterday.
Oh yeah. What? Which word was that?
Ooh, biquinary coded.
There you go. So that was a message-based protocol. You see, you can cover all paradigms with this. Okay. So system of representing numbers based on counting in 5s. I have no idea where that idea came from. Okay. Right. Counting in 5s. With an additional indicator to show whether the count is in the first or the second half of the decimal range. Whether the number represented in the range 0 to 4 or 5 to 9 or 1 to 5 and 6 to 10. Okay, so where do we see this? Well, you see this in classic abacus systems, like the professional abacus systems, not the ones you give to your kids, which actually have 10 beads. You have a 2 and a 5 system. Okay, it was actually used in the Colossus computer at Bletchley Park. Before they figured out that binary was a lot easier to do. Perhaps one of the best known ones is the Roman numeral system, one of the other classic katas. Now there is a fabled tale, which I wish were true, but I don't think it is, that actually the letters of the Roman numeral system came about visually. In other words, they corresponded not originally to letters, but to indications that you could do across a marketplace. So obviously 1, 2, historically, you would actually do 4 rather than IV. But if I want to show that something's 5, then that's 5, okay? And then That's 10. Okay, and you see this all works beautifully. There's 50, there's 100. I want this to be true. I don't think it is, but I want it to be true, okay? However, we don't have to worry about the truth of such things because we're going to do this enterprise style. We're going to just do this one thing at a time, and we're going to build it up, and we're going to do this, and yeah, okay, let's try that. Change the font size. There you go. Brilliant. Okay, if you're being paid by the line of code, this is magnificent. Okay, this is how you earn your living. But it is entirely possible you may spot some regularity, I hope. Now, one of the things I find interesting is a very subtle observation, and I noticed this when teaching my younger boy a little bit about programming, is that if you ignore the else, then an if is just a single one-time, is a limited form of while. You can normally, there's a lot of fun to be had trying to express one control flow mechanism in terms of other control flow mechanisms. And an if is simply a while with a very limited range. Okay, it'll execute 0 or 1 times, whereas a while will be 0, 1 to n. With that regularity in mind, you can condense it down to a lookup. Okay. Now, what is interesting about this is that obviously the declarative approach, there's this very simple idea that if you show me your data structures, then I can tell you what your program does. If you show me your data, your control flow, I will struggle. It's kind of obvious what we're doing there. And we've actually separated this out. And what is interesting is this kind of separation is actually quite fundamental in the large to a lot of software systems. I have a lookup and I have a way of processing it. Processing, thing to look up.
What's a double divisor? Like integer?
That is proper division done the integer way. It's kind of like divide. No, I really mean it. You know? Yeah? So yeah, this is integer division. It turns out that the idea of polymorphic division based on types in a dynamically typed language is fundamentally flawed. But it's taken a few decades to discover that. So here we have a simple way of ripping through a lookup. And now what we've got is 2 areas of focus, stability. Funnily enough, this actually looks like a message processing loop that I wrote many years ago. It was just like, yeah, I can do it all through a table. And then suddenly we have a completely stable piece of code that is comprehensible, and then a tabular representation that is extensible. I don't expect to be extending the domain of Roman numbers, but nonetheless, there is a fundamental idea here. Now, this is all well and good, but I mentioned John Jagger before, right at the beginning. He came around to my house a couple of years back, and we did some coding, and he said, oh, I came across a new solution, an alternative solution. It was an F# solution to the Roman numerals problem. And I thought maybe we could try it out. And so we tried it out in Ruby. I'm not really a Ruby guy. No, I'm not a Ruby guy. There's no really about it. I'm not a Ruby guy. I can read bits of it, and then I look at the rest and go, you're kidding, right? So I translated it immediately into Python. But it's elegant because, again, we've got another problem here that looks like an arithmetic problem, but actually it isn't. What we're going to do is if you thought binary was the fundamental counting system because your programs, you think binary, you know, that's it. Unary. Unary is more fundamental. Unary is the base that the universe uses. Okay? It doesn't have a condensed form. If I've got one thing, I've got one thing. If I've got 2 things, it's 2 things. This is 2 in Unary. Okay? This is 3 in Unary, you see? 4, 5. You've got 1 billion stars? Yes, there's a lot of them in Unary. One thing at a time. So what I do is I take the number and I convert it into Unary. You give me the number 323, I multiply I by it. I've got a 323 i's, okay? Unary is fundamental. Perhaps it's not very Roman though, so we reduce it little by little. We condense it down, we pipeline it, we filter it. We cook it down. No, I'm not making any claims for its efficiency, but I am making massive claims for its elegance and, importantly, its explainability. Because interestingly enough, good experiment, I tried it with my kids. I showed them this version, and then I showed them this version.
How old are they?
The older one's 15, the younger one's 11. And so, you know, they still have the desire to go and look at something else that's got a screen and doesn't involve dad. But, so there's a patience limit, but you can actually show, it's just like, oh, okay, that makes sense. There's an elegance here. It's just like, yeah, I quite like this. John emailed me the other day, he'd been messing about with it as well. He decided he wanted to try a different variation, so he decided to just focus on I's, X's, and C's. We could also factor that out. 10, 9, 5, 4, 10, 9, 5, 4, 10, 9, 5, 4. There's lots of different ways of showing the regularity. There's a lot of elegance to be had here. Although the disappointment here is we've reintroduced multiplication in lots of locations. But actually, no, that's good, because we've done no division. And it's string multiplication anyway. So there's a very simple idea here about thinking this is not actually an arithmetic problem. It is a symbolic manipulation problem. And there's a different way of looking at it. So we may say, okay, well, yeah, Python, but that's not really, I need to do proper functional programming, so let's do this in Clojure. And this is why this is also talk about style, because it turns out that not everything has a uniform, easy-to-access style. So if I do a straight translation into a standard applicative language model, then I end up with this. Let's change the font size on that. Yeah. It's got that kind of, it's got sort of, maybe it looks like an airplane. I don't know, what do you think? Maybe it's geese migrating in the winter. There's lots of choices here. Comprehensible? Not so much. So the straight applicative model is not the one we want. So we need to do some composition. In other words, we need to start thinking in terms of higher order functions. So what we're going to do here is two changes. One is I'm going to use anonymous functions, lambdas, but not spelt lambda. Okay, see? This is the creativity. If you're going to invent a language, don't spell lambda, lambda, all right? Either let your cat walk across the keyboard, let your kids pick a random emoji, or just rip all the vowels out. It's a function. No, it's a funk. It's a funk. Fung. Got it. Brilliant. We'll do it. Feel free to use F next time, because everybody will understand what you mean, okay? Okay, so now what we do is we've got a different model here, okay? So we've got composition. Okay, so first of all, we join. This is our unary converter. Then we successively, there's a problem with this. The problem here is that we are reading from the bottom to the top. Now, every now and then, a Lisp programmer or a Clojure programmer will come along and say, no, it's perfectly natural. No, it isn't. They are wrong. They are trying to sell you something, okay? Because in the same code base, you'll have things that read from top to the bottom, and in other places, you'll read from bottom to top. I don't mind which order, just choose one. So here, there's a notion here of like, yeah, I've got the elegance, I've got the power, but it's going against the grain of what I want to do in terms of pipelining. So, okay, let's simplify it before we get there. Now it's beginning to look much more like a table, so a little few abbreviations we can throw in. Then I'm going to use a threading operator, and I'm actually going to go back and use the member replace, just to keep it simple here. And then we've recovered that, but we've got a very different way of looking at it. And what is nice about this is I'm no Clojure programmer, but it doesn't take a lot to explain this. What is interesting about a number of these solutions is their explanatory power. It's the idea that it's not that you can read it immediately, but it takes very little to unlock it. If you look at the if-else-if versions, if you look at these complex control flow versions, they take a lot more deciphering. Here, you can show somebody who doesn't even program what you're doing. You can just walk them through it and they go, aha, it's easily explainable. Explainability is a very often overlooked power or quality of code. So there's a really important idea here. Richard Feynman. We could, of course, use any notation we want. Do not laugh at notations. Invent them. They are powerful. In fact, mathematics is, to a large extent, invention of better notations. Okay? There is a very simple idea. Sometimes people go, oh, syntax sugaring. It doesn't really change. It does change things. It changes things profoundly. Certain symbols, whether we are talking about moving from Roman numerals, which really are quite difficult to work with, okay, to the Arabic model, which is positional and is much easier to work with, it makes things easier. There are notations that allow us to stretch further. And what you're doing when you program is inventing a language to talk about your problem domain. Okay? So feel free to push out a little bit. Don't go too crazy, but if you're going to do it in a kata. It's a perfect place to experiment. It's a small, self-contained laboratory for techniques. Now, if we're going to talk about notations, and I've been talking about pipelining and things like that, I did think I would have a go at doing this on the command line, just for fun. Roman 42, XLII. There we go. There's my Unary converter. I was very pleased with this. This is hideously inefficient, so we can actually put it all in sed. So there, it really is just text manipulation. It's a text manipulation problem. It is not an arithmetic problem at all. You thought it was about numbers. It's not. So again, there is something profound here that is basic to all programming, where you convert a problem that looks like this into a problem that looks like that. Oh, you told me it was a number problem. Actually, it's not. Or rather, I can show you something else. Let me take that problem, and now I understand it, turn it through 180 degrees and then an imaginary amount, and I will give you something else that you did not think of before. And it will provoke thinking. That's the whole point of these. So, I will end with Stuart Brown's quote. We talked about style, we talked about form. Style is times form is times student. Form is ultimately what you're after. Form embodies understanding. When we use the term kata, it is not simply a training exercise of repetition, which is good. That's the basis of it. It's practice, but it's also an opportunity to experiment. And sometimes we overlook the second part of like, okay, I think I know this. I showed this to a friend of mine who's a mathematician. And she kind of came up to me afterwards and said, okay, two things. One, I didn't know there were that many proofs of Pythagoras. Two, I thought I knew the Roman numerals solution. Okay? There is always more, and there always will be more. Thank you very much. Okay. We done? A couple of questions, maybe? Yeah? Yes?
10954, you saw that pattern
yes.
over and over. Have you ever thought of writing it as a kata to extend Roman numerals?
That's really interesting. No, that's why I do this, because now you give me an idea. That's great. I love it.
The letters always come in threes, right? IVX and then X.
Yeah, there's a regular patterning, and once you've seen it... Yeah, sorry, 10954, there is this recurring pattern. What about extending Roman numerals? Okay, so therefore, let's just imagine a kind of... People love the alternative timelines. What if the Romans had kind of gone on for a bit longer and had decided that they'd keep their number system and decided that numbers were not big enough? How would we extend this? You could make it regular. You could create your own number system based on this biquinary coded decimal system. Have an extension.
You call it the Bar-Kokhba system. If you're revolting against the Romans.
Oh yes, yes. But actually, I think I might go for the Eastern Empire because the result will be quite Byzantine. Okay, right. Another question. And feel free to do an extended Roman numerals card. I've never thought of that. I've seen extended Fizzbuzz. I've not seen extended Roman. That's great. Any other questions, thoughts, reflections, desires for beer, desires to play Fizzbuzz? I mean, you've got to be practical, haven't you? I've just shown you the theory of Fizzbuzz.
Well, can I share something now? I wanted to say to you afterwards. Last night I saw one of Tom Scott's videos, and he talked about solving Fizzbuzz. Yeah. So I spent a good couple of hours of sleep just writing other solutions for it. So I just wanted to
yeah, it is quite fun because it's a self-contained problem. You'd be surprised how much you can come out with. And occasionally, a spark of inspiration comes along and goes, you know what, I think this could lead to something else. It makes you look something else up. You learn more of the language. It makes you say, what about this language? What about that language? It causes you to do things. It creates a chain reaction. Occasionally, people say, but how can I use this in my everyday code? My answer is, I don't know. You tell me. Okay, that's the idea of play. This is a really important idea. So play is a very is fundamental to this whole concept.
Yeah, I said that it depends on context because sometimes you'll have more than one to one. That is not the question you want to solve. That is an example of the question you want to solve. So sometimes you'll have more than 100 numbers, but if you have more numbers that you can contain in memory, so you generator.
So yeah, change the context, and there's actually some very good examples. Yeah, change the context, change things like the sizing of the domain. What if it's 1,000? What if it's 1,000,000? Okay.
What if it's not 3 and 5?
Yes. Yeah, there are Fizzbuzz variations that do other things. In other words, there's lots of possibilities of variation, and each one points in a different direction. It was actually a very interesting example I did at a company. It was bigger than this, bigger than these ones. It was actually a programming contest example. It was a phone number lookup approach, phone number prefix lookup approach, and it was interesting because 4 of us had an approach. We did it in Python, and it was for a workshop, and we wanted to show 4 fundamentally different approaches. So I went for an approach that was minimal, Pythonic and functional. Somebody else went for an approach that was massively efficient, used trees and all kinds of stuff. Somebody else decided to just do it in a scripting style. You know, in other words, I will do Python in the manner of a scripting language, just pure scripting approach, sort of classic procedural scripting. And then somebody else did an in-memory approach. And it was interesting, if you change the parameters of the problem slightly, then it became completely impractical. But memory is one of those things that, you know, we seem to be getting more of. Because it turns out one of the things that we have learned is you can't beat the speed of light. Okay? Unless you have all that exotic matter, you know, if you have it, then, you know, what are you doing here on Earth? It turns out that the network is always going to be slower than your local memory. So therefore, if you have more local memory, it turns out you can do a lot more computation. So this idea is that his solution would scale given enough years. Yeah? And that's not a stupid idea, because if we look at many of the solutions that we now adopt, if you go back 10 years, go back 20 years, it's just like people would say, you'd never be able to run that in memory. That's impractical. Oh, we're doing it all the time now. So these things change. Yes?
Sleep sort.
Oh, sleep sort. I love sleep sort. Sleep sort is one of the most counterintuitive and yet profoundly elegant ways of doing something. Has anybody come across sleep sort? This is off. I'm going way off slide here. Sleep sort is I have an example. I think I have an example. It is beautiful in a way that is insane.
It will also scale up in a few years.
It will.
Better resolution timers.
Yeah, there is something quite beautiful about it. Oh yes, there we go. Here it is. Okay, so here is my reduction of sleep sort. Sleep sort was possibly the only good thing to ever come out of 4chan. We don't know who invented it because it was an anonymous poster. They posted a much more complex version. I've reduced it down to actually straight Bourne shell. You don't even need bash. So we've got that, and then, okay, let's execute it. And what we're going to do is we're going to sleep sort the first few digits of pi. 1, 1, 3, 4, 5. Wait for it.
This is the same as noodle sort for quantum computers.
Do you know, I'm going to have to look at that, because this one has certain properties. I guess one of the properties it shares with the quantum computation. Actually, no, the quantum one should be 01. This is linear.
You know spaghetti sorter, right?
Yes.
Take a handful of spaghetti and just throw them down.
I've got lots of sorting algorithms on this particular slide deck. You know, if you're really interested in, you know, really bad sorting algorithms, I've got them. You know, here's a permutation-based approach, which is factorial complexity. I use this one. People say, oh yeah, we don't have any performance requirements. You know the best way to find out people's requirements? You give them something like this, and then suddenly they will discover they have requirements. Okay, it's just like this has got factorial complexity. Then we've got BOGO sort. I didn't put any of the other ones in, which just uses random. Take a sequence, shuffle it. Is it sorted? No. Shuffle it again. Keep going. The complexity of this is OMG. So, yeah. There's a whole host of these things, but they are all provocative, they all do something, they get you thinking. And sleep sort, I just love the nonsense or the insanity or the elegance of sleep sort, because this whole idea of it's actually linear, but it shows you that you can now farm all of these processes out. If you have all of the stuff available, then everything is a processing node. You just have to scale the time appropriately, because it turns out that the linearity, logarithmicity or quadraticness is actually not your problem. It turns out it's a different problem, but it makes you understand that performance is not simply a property of complexity. But yeah, so, you know, there are some really insane things out there. And on that note, we're done. Thank you.